So, ready guys? Yesterday we said that the sine and the cosine behave the same. And they're continuous curves, but the tangent and the reciprocals are not continuous curves. So because they're not continuous, there's something there that stops that curve from continuing. And that's an asymptote. So what an asymptote does also is put a little break in your domain. So the first thing we did with your tangent was we took a look at your unit circle, and everything is working off the unit circle again, just like it did for sine and cosine, because in the sine and cosines, that gave you your maximums, your minimums, and your zeros. So we're still working off of that. Now we said tangent is y over x. Now, if you divide by a 0, if x is 0, we have an undefined situation because we can't divide by 0. So we looked at where is x 0? Not here, up right here, not here, up right here. So we decided that, okay, I have an asymptote here. It's a stop. I can't go past there because I don't have a tangent. So we kind of laid these out and we said 1 pi over 2, 3 pi over 2. What would be the next one? What pattern do we see?
5.
5 pi over 2. So, and then 7. Good. So we see, so we see a pattern. So we said any of the n pi over 2, where n is an odd integer, will stop my graph. Agree? Because we have a -1, a -3, a -5, a -7 over 2. So that's going to stop my graph. So my tangent curve is going to go like this in between these sections. And it made its own natural boundaries. And we can tell, therefore, that the period of a tangent curve is not 2 pi, but pi. Okay? Because it's got its natural boundaries here. So we write our domain as real except when x is equal to n pi over 2, where n is any odd integer. This is how we have to define our domain. And if you forget, you just look for the pattern. Our range, we said, was all real numbers. Agree? We did the range yesterday too, all real numbers. Now, we then took a look at cotangent. I'm just redoing what we did yesterday. So again, here's your unit circle. Okay, so now my cotangent says x over y. So now, if my y is a 0, I'm going to have an undefined situation. So I look at my y's. Whoops, there's a 0. That one's okay. There's a 0. So I notice, and they're always 180 apart, right? Because isn't the period 180? 180, that's what gives me the period of 180. So I stop at the 0, can't get through there. Stop at the pi, can't get through there. What would come next? 2 pi, good. And I got negative pi. And I got negative 2 pi. So, any 1 pi, let's go to 0 pi. 0 pi, 1 pi, 2 pi. What would come next? 3 pi, 4 pi. So how could I say this with an n? Any integer. N pi, and n is any integer. Good. So that's how you define your domain. Now, our tangent curve works this way. Your cotangent curve works this way. It still has a period of pi. And our domain, you have a lot of them. They came accidentally last time. Continue this. So now, we're going to write our domain as real except x is equal to n pi where n is any integer. And what's my range? Where's my lines going? Infinity. Negative infinity, positive infinity. Okay, so we can figure this out for ourselves, and we don't have to memorize them, right? Yes.
So the I was saying, so the is it the same every time?
Well, for cotangent and tangent, yes. Now, we're going to do the reciprocals. The reciprocals of sine and cosine. And we're going to find they have a little pattern too. So we left off here yesterday. What is cosecant the reciprocal of? Sine. So I'm going to start and just put a little sine curve out here. I'm just going to put it in dotted lines. My sine goes 0, 1, 0, negative 1, 0. So 0, 1, 0, negative 1, 0. So it's going to look like this. Right? And I'm going to just bring it the other way. This is my sine curve, right? Now, when we looked at your unit circle before, we looked at your unit circle for tangent and all of those, and we said whenever we divide by a 0, we have an undefined situation. So what happens here is, all of your zeros, what happens when I take the reciprocal of 0? If I'm going to take the reciprocal of 0, right, I'm just going to put it over 1.
Oh.
And when I take its reciprocal, I get 1 over 0, which I can't do, undefined. So here's the key. Just like the 0 in the denominator, all of your zeros are going to give your inverses, your reciprocals, a hard time. So all of your zeros are going to become asymptotes for their reciprocals. Remember, reciprocals say, take whatever that was and flip it over. So if I had the sine of 90, which is the sine of pi over 2, which is 1, and I take its reciprocal, what is the reciprocal of 1? 1. Its reciprocal is also 1. So at 90, my reciprocal is also 1. So all my 90s and my negatives, all my 1s, they will be the same reciprocal. Now, if I took the sine of 30, the sine of 30 is 1/2. What is the reciprocal of 1/2? 2 over 1. So here's my 30-degree angle. Here's my 1/2. So at 30 now, when I take the reciprocal, it's up here, isn't it? Right. So if I took the 150, I would be over here, the sine of 150, and it would flip over like this. So look where your reciprocals are going, like this. They're using these as boundaries, and they're coming down like this. These are your reciprocals. They're using your asymptotes as a boundary. It's almost like it's making a little parabola, but it can't go out of that boundary. So we plotted our basic curve, in this case our sine. We looked at the zeros because when I take the reciprocal of 0, it becomes 1 divided by 0, which we can't do. Those became our asymptotes. Then all we did was use that as a guideline. We're not writing anywhere near the sine curve. We're doing the opposite from the sine curve.
So the range would be 1 to infinity, negative 1 to infinity?
Almost. So 1 to infinity, 1 to infinity, and not negative 1 to infinity, but what? Negative infinity to negative 1, right? Isn't it the exact opposite of sine? So I'm coming from down here, negative infinity. I'm stopping at negative 1. Can I use negative 1?
Mm-hmm.
Yep, because that it flipped over to be negative 1. Then I'm going to jump all the way up here and start at 1 to infinity. That's good. That's good. You knew what you were saying. It just was backwards over here. Now, my domain says, take a look at what we cannot use. We couldn't use the 0. We couldn't use the 1 pi. We couldn't use the 2 pi. This has a familiar sound, right?
So we can't use any positive integers?
Oh, we can't use this either. We can't use the negative 1 pi. We can't use the negative 2 pi. We can't use the negative 3 pi. N is any integer. Good. So the domain says real except where x is n pi, where n is any integer. And which one was that like, the tangent or the cotangent? Oh, and they both begin with C. It was just like the cotangent one. And they both begin with C. That's a good way to start to remember it. Good question, or you just...
No, I
Okay.
thought mine was.
Okay. All right, so are we kind of seeing this? Okay. So anytime you're going to graph a cosecant curve, you're going to graph your sine curve first, and then you're going to put your asymptotes down, and you're going to build your reciprocals. Make sense? Okay. Last one is the secant curve. What is their secant a reciprocal of? Cosine. So we're going to come here, and we're going to do our cosine. So 1, 0, negative 1, 0, 1. We're just going to build our cosine curve. So 1, 0, negative 1, 0, 1. Oh, that's such a glare. So here's my cosine curve. Okay, so now, by looking at this, what angles are going to have an undefined secant?
3 and 3 sine
Pi over 2,
3
270, right? 3 pi over 2. What are we finding? The zeros, right? What else?
negative pi over 2 and how did you know that?
Because the zeros, anytime you have a 0 and you take its reciprocal, you put it over 1. As soon as I flip this over, undefined.
So it's always the 0.
Always the zeros. Always the zeros. And it kind of makes sense because now, when I flipped over the 1, it became a 1. And look where my reciprocals go. Same as the other one does. Obviously, they're just set 90 degrees apart here, but same pattern. Okay. So the range, what's the range for this?
1 and
Negative infinity to where?
to negative 1.
To negative 1.
And 1 to positive infinity.
1 to infinity. Good. Let's see if we can find the domain. Real except when x is equal to what? Say it again, Carlos. And not yet. But what do you have going on here? 1 pi over 2, 3 pi over 2, n pi over 2.
Jennifer, this field?
Yes.
You have to go to Mr. Woody.
Now?
So what's my pattern? N pi over 2, where n is any odd integer. Wait, let me give you the homework, Jen. Are you going to write that? Okay. Where n is any odd integer. Which one is that one like?
The tangent.
The tangent. So actually we only have two things. The cosecant and the cotangent have the same domain, different ranges of course, and the secant and the tangent have the same domain. Because if you think about it, we only have 4 quadrants. Either they're going to be like a pi over 2 or they're going to be a pi. So there's only 2 types of domain restrictions we could possibly have with our zeros, because they work right on your quadrants, right off your unit circle. So how are you feeling about this changes? But we're not going to panic. So we're going to say, okay, let me do where this came from. What is secant the reciprocal of? Cosine. So we're going to start like this first. What does this 1/2 do? By a half. So it takes it, not stretches it, but shrinks it down. Good. So my cosine is this. I'm going to multiply, like Owen said, everybody by a half. So I'm going to get a half, 0, negative a half, 0, half. I'm going to use this pattern. Okay, do I have any vertical shifts here? No. Okay, so now, what does this 2 tell me?
How many cycles there are in 2 pi?
In 2 pi, very good. So if my frequency is 2, I have 2 cycles in 2 pi, or 2 cycles in 360. So how long does it take me to complete 1 cycle? Pi, very good. So my period again is 2 pi over 2, or every pi. And how many quadrants do I have to go through every pi? 4. So let's start there. Let's break this up. Let's do our regular cosine curve first. So let's break this up, every pi, and break these into 4 equal quadrants. Here's half, and half of them put us at the 45. We don't even care right now. We're just breaking this up. Okay, so far? We broke it down into 45-degree parts, and we're going to do our cosine curve to the 1/2. So you might want to put a little bit of a mark in the middle there. So we're going to go start at the 1/2. Here's our pattern. Every tick mark that you just made. 0, negative 1/2, 0, 1/2. God bless you. Isn't this 1? Right? Now let's do this again. 1, 0, sorry, 1/2, 0, negative 1/2, 0, negative 1/2, 0. I think I'm off on this. So here's my 1. Okay, this is my 0 over here. 0. It's so hard to do this sideways. I have such a glare for some reason today. Okay, and then we could do the other side as well. Just follow your pattern all the way across. I like a spaz today. Okay, so now, that's our regular curve. We have to make our reciprocal curve from this. It fits my 1/2. It gives me 2 cycles in 2 pi. What angles are going to give me problems? Anything that has the zeros. So I'm going to take these zeros, and I'm going to put asymptotes here. Because as soon as I flip over a 0, I get an undefined value. Okay, now, from here, I can graph what I intended to graph, my 1/2 secant 2x. Here it is, right here. Just stay within this little alleyway here, if you will, and graph your reciprocal function. We'll check your domain in 1 second. See it? Got a lot of these. Don't you have twice as many? Because we did 2 times this, right? Okay, so now, let's work on our range first. Our original range of our cosine was now from negative 1/2 to positive 1/2 because we shrunk it down. What's my range for my secant curve? Negative infinity, where am I going to stop? Negative 1/2. Then where am I going to start? Start again at the 1/2 to infinity. Now, my domain. So when you look at this, this is how you say this to yourself. What's half of 90? 45. So this is a pi over 4. So let me count. This is every 45-degree section, right? So watch. 1 pi over 4. 2 pi over 4 was okay. 3 pi over 4 gave me a hard time. 4 pi over 4 was good. 5 pi over 4 gave me a hard time. Do we see a pattern? What's our pattern? N pi over 4, where n is what? an odd integer.
Okay.
So my domain says real except x equals to n pi over 4, where n is an odd integer. So we kind of found it ourselves, right? Now, there's an alternative way to solve this as well. We're going to take a look at the alternative way to solve this. Our original secant is just like our tangent. Secant and tangent work the same. And the original tangent says the domain is all real except when x is equal to n pi over 2, where n is an odd integer. Agree? So watch. Take whatever is next to this x, because didn't it used to say plain old x? So now I want to set 2x equal to this here. I'm going to keep the same thing. All I did was take the original one. Instead of x, I have 2x. So I need to solve for x. I need to divide by 2. When I divide by 2, I flip this over. So it becomes n pi over 4, and I keep the same qualifier, where n is an odd integer. So here's my domain. Real except, and isn't that exactly what we found when we looked at it? So algebraically, you can find this, and you're going to have to be able to do this without graphing it as well. You're going to take the original one, and we'll do another one. You're going to take the original one, and you're going to set it equal to whatever it is here, and see where your domain should be. Does it make sense, though? Mm-hmm.
I have to do that again, though. Algebraic, algebraic.
Yeah, we'll do another one. But are you comfortable with this?
Yes.
So basically, all I want to do is go back to my original, paragraph, graph that, find my zeros, there's my asymptotes. Pretty much all you got to do is just make those little parabolas in between the little outerways, and you got your reciprocal functions. Okay? Question? Question? No? Okay. Let's try another one. So say I give you one that says okay? I give you one that looks like this. So just kind of on that paper anywhere, just let's do this one together. What is my graph, my original graph?
Sine.
Sine. So I'm going to graph this guy. I'm going to just start like with your 90s. Pi over 2, pi, 3 pi over 2, 2 pi. Okay, so we're going to graph our sine curve. And what does this 2 do to my sine curve? Stretch, vertical stretch. I'm going to multiply everybody by 2. So I'm going to get 0, 2, 0, negative 2, 0. So now we're going to have to put 2 tick marks in here. 2 and 1. Okay. What does this 1/2 do? Half the cycle into pi. Half the cycle. So if half of my cycle is into pi, how long is it going to take me to complete an entire cycle? 4 pi. So doesn't that make sense? My period is 2 pi over b, 2 pi over 1/2, keep change flip. It's going to take me 4 pi. The sine curve is cute because it goes half and then the other half. But our other half will bring it to the negatives. So if you're doing this, how many quadrants have to go through 4 pi? 4. So every quadrant is pi. So let's just start your sine curve. So we have at the 0, at the pi we have a 2, At the 2 pi, 0. Then bring this backwards. At the negative pi, negative 2, 0. So here is your original sine curve. I'm a little madness. It's very hard to go sideways on this board for some reason. And I'm getting such a bad glare in. Okay, so now, where do I look to see where my asymptotes are going to be?
Where the zeros are.
Where the zeros are. So I see a 0 here. I see a 0 here. I see a 0 here. Okay? So I make my reciprocal now. Here's my little guidelines, and all I have to do is this. There's my reciprocal function. Don't forget to graph it. There's my reciprocal function. That's it. So I can't have two of them on each because I did half of the curve in 2 pi. Now, what's my range for my reciprocal?
Negative infinity to negative 2.
Good. And 2 to infinity. Good. Now, let's look at where your domain restriction is. Domain says real except. I notice I'm at the 0 pi. I notice I'm at the 2 pi. Where else would I be? 4 pi. So, what's happening here?
All the full.
The even numbers, but I never had one that said even numbers, right?
Right.
So they either said every odd number or every integer. So technically I know that it's real except, and if you want to start like this is a good way to start, n pi, where n is any even integer. But I didn't used to have even integers. I only had odd or every integer. So if I wanted to go, I'm obviously can't do the odds. So if I wanted to go n is any integer, what could I change this to make it be even? So if I put a 1 in here, what do I have to do? Multiply it by what? So here I am, 2n pi, where n is any integer. If you left me this, I probably would not mark it wrong because it's true. That's what it is. You're even, and 0 is an even integer. But we like to stick with this, and I'll show you algebraically in a minute why we stick with that. But this is not wrong because you are doing the even integers. If all else, at least follow your pattern. Now, if we set this equal, we look for our cosecant. Our original cosecant was just like our cotangent, remember? Was real, except when x was equal to n pi, n is any integer. Guys, stay with me. Now, instead of x, what do we have? 1/2 x. So I'm going to replace that with 1/2 x. Just replace this with the whatever it says there, and solve for x. So when I divide by 1/2, doesn't this flip this over? 2n pi, and there's your qualifier. N is any integer. And isn't that what we found? If we kept with our regular? It's the same as your even ones.
So your domain is all real except your asymptote.
Yes. Yep. Real, and we write it except. Because those are the ones I can't go through. That's what causes the break in my natural curve. It says, look, barrier, can't go through it. And your asymptote becomes your domain restriction. Good? Does this make sense?
Yeah.